All right, this video is for calculus, and it's on the unit where we cover parametric equations, polar coordinates, and vectors. We're going to start with a quick introduction to or a review of conic sections. This is a topic that's taught back in pre-calculus or honors algebra 2 or similar class, but we need this because at various times throughout this part of the course, we're going to need to be able to quickly sketch the curve shape of conic sections without a calculator. We just want to review how to do that really quickly. So the topic here we're going to cover is not going to be as completed as it was covered in the previous classes, because all we're really interested in is how to quickly sketch. But just quickly to remind you, a conic section is a two-dimensional curve, which is the intersection of a plane with a cone in 3 dimensions. So if you have a plane that intersects this way, perpendicular to the axis of symmetry, you get a circle. If it's offset, you get a parabola. If it's offset not quite as much, you can get an ellipse, and if it's straight up and down, you can get a hyperbola. They all have equations of the general form where there's a squared term for x and y, and the non-squared term for x and y, and a constant added up to 0. It is possible to have something with an xy term, although we will not look at those forms because they're tilted. Their axes are tilted, and we have to have different mechanisms for those. And some of these terms may be missing, but it's terms which have x's, y's, x squareds, y squareds, and constants, or some combination of those things. And then there's 3 categories: parabolas, ellipses, of which circle is a special case, and hyperbolas. And each one has a different standardized form for the equation and different ways to graph them. So I'm going to review those quickly and work 2 examples of each in this video. Okay, so let's start with the parabolas. The parabolas open up one in one direction, like for example, y equals x squared is a parabola, right? If you have something like that, it opens up this way. If you have something with a negative, so negative x squared, it opens up this way. If you have something in the form x equals y squared, that opens up this way, and x equals negative y squared opens up this way. So in general, you have the rough idea of the shape, but exactly where the places that the curve changes direction, which is called the vertex, and how wide the object is depends upon the specifics of the equation. So there is a standard form for the equations, and it's this. If you have the x squared type, usually we put this where the squared term is on the left, and then the non-squared term is on the right. So it could be either x squared or y squared, and then the other term would be the non-squared term. And you arrange it to have x minus h squared, y minus k, where hk is the location of the vertex. Okay, and then this p here, 4 times p is whatever the multiplier is. If that 4p is positive, then it's opening either upward, in this case of the x squared, or it is opening to the right if it is this type where the y is being squared. If it's negative, it's opening up in this direction or in this direction. And then that p is a specific distance. So what's interesting about it is, if you locate where the vertex is and you know where this is opening around, you can go a distance p in that direction towards the inside of the parabola. And then if you go a distance of 2p on either side, you get to 2 other points that are on the parabola. And that gives you the vertex plus 2 points to quickly sketch this. What makes this a parabola is that the distance, all the points on the parabola, are equidistant from the focus point and from this line, the directrix. And that makes this particular shape useful for focusing energy, like antenna dishes, flashlight reflectors, and things like that. Okay, but what we're focused on is how can we take an equation that's in this form right here and put it in standard form so that I can quickly graph it. All right, I can see there's an x squared term and then no y squared term. So with only one term squared, that makes us a parabola. The x squared term or the x term is the one that's squared, so I'm trying to put the equation in this form. So what we'll do is we'll take the x parts, the terms that have x, and leave them on the left, and then move the others to the other side by adding them over to the other side. And then we're going to do a procedure called completing the square. So the way completing the square works, let me show you on the side with a different example. If you have, let's say, a perfect square, like x minus 3 squared, that's the same as x minus 3 times x minus 3. And if you do FOIL, the distribution procedure, you get x squared minus 3x plus 9. And then these, because those are doubled, becomes x squared minus 6x plus 9. Okay, so what completing the square does is basically reverse that. So let's say that you had just a portion of that. So let's say you just had x squared minus 6x, and you wanted to complete the square like we have over here. What we're going to do is we're going to say, I know that there's something here that I have to make this what we call a perfect trinomial in the form that will match this. And if you notice, the value that's in the middle here, this minus 3, is just this minus 6 cut in half. So what we do is we write the pattern for a complete square. We just copy this letter here, but the letter that goes, or the value that goes here, is half of this value. So you cut this value in half with its sign. And then the value that has to go here is this minus 3 squared, which is plus 9. That happens because we're multiplying those two things. So take the middle number with its sign, cut it in half, square that number and put it there, and you've made a perfect trinomial to match the perfect square so that we can rewrite it from that form to this form. So that's what we're going to do. We're going to make a perfect square on this side so that this matches this form over here. And we're going to do that by cutting this negative 6 in half to negative 3. When we square it, we'll get a plus 9. I like to double underline it because I added that to the left side, which means to keep this equal, I have to add a 9 to the other side to balance it, which means now I have a new number out here. This is 8y plus 16. All right, so now at this stage, I've got x minus 3 squared on the left equals 8y plus 16. I'm going to factor out that leading 8 to leave y plus 2 there. And now this is exactly in the form x minus h squared equals 4p times y minus k. Okay, so now I can identify what the things are. The hk is the vertex. So that means the vertex here is at, let's see, the x coordinate is 3, right? And the y coordinate is, this x plus 2 can be thought of as y minus negative 2. So that's a negative 2. And that locates where the vertex is, right? The other thing is that this number 8 is to be equal to 4p. So since 4p is equal to 8, that means p is equal to 2. Okay, so how does this help me in sketching? Well, when I sketch, what I would do is first locate the vertex. So the vertex is at positive 3 in x and negative 2 in y. I'll put a dot there. And then I have to figure out which direction this opens. This is y equals x squared, right? So basically looking at this, we have a squared type, which means it's either opening up or down. And because this 4p number is positive, it's this one, it opens up. So I know that this is going to open upward, right? So what I do is I go this distance of p upward in that direction, so up to this point, and then I go 2p over in the other direction. 1, 2, 3, 4, there's another point. 1, 2, 3, 4, there's another point. And those 3 points, so the vertex and these 2 points are on the parabola, and that allows me to sketch the parabola in reasonably accurately. Okay, so this is how you put a conic section equation into standard form so you can sketch. All right, let's do one more example of the parabola. This is another parabola. I've got the y squareds here, so what I'm going to do is actually, since they're negative, I'm going to get them over to the other side. So I have 4x minus 9 equals y squared plus 2y. When I move this over, then I'm going to change directions because we put the square term on the left for a parabola. And then I'm going to complete the square. So that means I've got, let's see, y, this is going to be y, right? So to complete the square, I take this 2 and cut it in half with its sign plus 1. I square that number and add it on the left, which means I have to add it on the right as well. And so therefore I get y plus 1 squared is 4x minus 8. That means y plus 1 squared is, if I factor out the 4 times x minus 2, which means the vertex is at 2 because this is the part from the x. That's the x coordinate. And y plus 1 is the same as y minus negative 1. And then since 4p has to equal 4p equals positive 1. All right, so since this is a y squared type, that means it would open either this way or this way. Since this is positive, it's this version. All right, so now I'm ready to start sketching. I would make my sketch, x, y. Let's say I have to go to, let's see, x is 2, y is -1. So here is a point that is on the parabola. Right? Then I'm going to go a distance of, let's see, p is 1. So I'm going to go a distance of 1 in this direction, and then a distance of 2p up and 2p down to get to two other points that are on the curve here. So that, and then I'll draw my curve through those points. So here is the parabola, something like that. All right, that's it. That's all there is to it. So that's how we deal with parabolas. Okay, the next shape is an ellipse. And an ellipse has a standard form, but this time we have an x squared term and a y squared term, and they're both the same sign, so they're both positive, okay? So we also have a structure where it's x minus h and y minus k, except that the hk in this case is the center of the object, right? And then the number below the x is, if you think of that number as being something squared, so 2 squared in this case and 3 squared in this case, that means we go a distance of 2 in the x direction, and we go a distance of 3 in the y direction from the center to get the other 4 spots that are on the ellipse, and then you can sketch the ellipse in there. Okay, we don't really have to worry about like in honors algebra 2 they talk about this one's called A and this one's called B and all this other stuff. We don't really need that. We just need to figure out where the edges are so we can quickly sketch. Geometrically, what makes this ellipse is if you were to take a string, there's actually 2 special points inside the ellipse called the focus points or the foci. And the ellipse is the trace of all the places that the sum of the 2 distances from the point on the ellipse to the 2 focus points, the sum stays constant. So it would be, imagine if you had a string and then you move this along, stretching the string out like that, okay? Its application is in astronomy, one of the applications, because orbits are always elliptical. So the moon orbits the Earth in an ellipse, the Earth orbits the sun in an ellipse, things like that. And then there's the C is part of figuring out where the focus points are, but we're not concerned with that. We're just concerned with the sketching. Okay, circles are a special case of ellipse. So if the distance from the origin is the same in the x direction as the y, these 2 numbers are the same. So you end up multiplying that over to the right side, and that becomes the radius squared. Okay, so the standard form of a circle is a modification of the ellipse form where you've taken this bottom number and multiplied it across. All right, and of course we use that a lot for trigonometry. All right, let's take a look at a couple of examples. In this case, we can start with this one. I can tell this is going to be an ellipse because I have an x squared term and a y squared term, and they're both the same sign. All right, so what we'll do is we'll gather the x terms together. So 9x squared minus 36x. I'm going to leave some space because we're going to complete the square. Then we have 4y squared plus 8y, and we'll leave some space to complete the square, and I'm going to subtract the 4 to the other side. Then we're going to go ahead and complete the square for x, and we're going to complete the square for y. Before we do that, sorry, we need to do one other thing. Before we do that, we're going to factor out any leading number on the x and the y. So if we factor a 9 out here, we have x squared minus 4x. And I'll leave some space in there so I can complete the square. And then I'll factor out this 4. That'll leave y squared plus 2y. There's a y there. And I'll leave some space to complete the square. So now we're ready to go. We're completing the square for the part with the leading coefficient of the squared term factored out. So this means we've got 9x, and then we're going to get a perfect square here. We've got 4 and then y, and a perfect square there equals -4. Right? So that means we're going to have this. We'll take this -4, cut it in half. That's -2. Square that number, which is +4. Now this 4 is multiplied by a 9. That's 9 times 4 is 36. So since we added 36 on the left, we have to balance that with 36 on the right. And then we'll do the same thing for the y. So if we take this +2 and cut it in half, we get 1. That 1 squared is a 1, so I'm going to put that here. But that 1 is times a 4, so we've added 4 on this side, so we have to balance that with 4 on this side. And that means that now the new number on the right is 36, because these are canceling. All right, so now this is in standard form, almost, because for an ellipse, we have to have a 1 out here. So the last step, we're just going to divide everything by 36 to force there to be a 1 over there. And that means that 9 divided by 36 means that 36 divided by 9 is 4. So this would be x minus 2 squared over 4 plus y plus 1 squared over 9 equals 1. Okay, and we're going to think of this 4 as being 2 squared and this 9 as being 3 squared. All right, now we're ready to go ahead and find the center. So the center here is x minus h, that makes that 2, and y minus -1 makes this -1. Now we can sketch it. So if we sketch it, we'll start with locating the center of the object. This is at 2, -1. So this is the center. It's not a point on the curve, right? But then what we'll do is go a distance of, let's see, under the x here, we have 2 squared. So that means we're going to go 2 in the x direction, 1, 2. That point is on the curve, and 2 in the x direction this way. That point's on the curve. For the y, that is above this 3 squared. So we're going to go 1, 2, 3 up in the y direction, and 1, 2, 3 y in the y direction there. And then we can go ahead and draw in the shape. The shape is an ellipse. Right, so there we go, a quick sketch of an ellipse. Okay, here's another one. If you wanted to, you can pause the video and try this one. But let's go ahead and try it. So we'll gather the x terms together, 2x squared plus 12x, and then plus 2y squared minus 16y. I'll move the rest of the constant to the other side. We'll factor out the leading 2. So x squared plus 6x will leave a spot there for us to do our complete the square. We'll factor this 2 out as well. Y squared minus 8y, and leave some spot there, -40. All right, and then that means we've got to get perfect squares here. So we'll do set up for perfect square, y. Right, and then to do the completing the square, we've got to take this 6 and cut it in half to get a 3. And then take that 3 and square it, which will make a 9. But 9 times 2 is 18, so since we put an 18 on this side, we have to balance it with an 18 on this side. And then the same thing here, we'll take this -8, divide it by 2 to get -4. -4 squared is 16, but 16 times 2 is 32 was added to the left, so we have to balance with the 32 on the right. And that turns out to be, make sure I don't get the wrong number here. Turns out to be 10, yeah. So now we have a new number on the right side, which is 10, right? Because this has the same number here and here, that means instead of dividing the 10 and making there 1, we know that this is actually the special case of an ellipse, which is a circle. So instead, we'll divide everything by 2, and we'll get x plus 3 squared plus y minus 4 squared equals 5. That means the center of this circle is at -3, +4. And the radius of the circle is the square root of 5, because this number out here is the square of the radius. Okay, now we can graph it. So we can make a graph here. Let's see, we're going to go to -3, 1, 2, 3, +4, 1, 2, 3, 4. This is where the center of the object is. And the radius is the square root of 5. The square root of 4 is 2, so this is a little more than 2. So I'm going to go a little more than 2 in all the directions, and just draw in a circle that has that radius around that location. All right, so not too bad. That's how we sketch a circle. We started out as an ellipse, and we just do one last step that's different. Okay, the last shape is a hyperbola. Graphing is a little more complicated, but still just kind of a variation on the theme. The difference between an ellipse and a hyperbola is that in an ellipse, we have the exact same standard form, except that we have a plus here, which means both of the terms are positive. The difference here is that we either have the x term is positive and the y term is negative, or we have the y term is negative and the x term is positive. So because of this minus in between, right, one of these two terms is negative, okay? But the graphing is almost the same. We still have a center, which is at hk, where the h is wherever the x is. And then we still have a number down here, which is interpreted as like something squared. So it could be 2 squared, 3 squared. We still go from the center. Whichever number is under the x, we go that distance away. So let's say this is a 9, which is 3 squared. We would go 3 in the x and get a location. And then we still go 2 in the y in this case. The difference is, instead of just filling an ellipse into that box, we draw out a little box. I draw it with a dotted line. And then we draw asymptotes through the center and the corners of the box like this. And then the hyperbola actually starts on the major axis that we call the transverse axis at the edge of the box, and it goes this way to eventually align itself with those asymptotes. And which axis we use depends upon which is the positive term. So if the x is the positive term, then that means that this is opening in the x direction, right? If the y is the positive term, then it's opening in the y direction, okay? And geometrically, this is similar to the ellipse. The thing is that instead of the sum of the distances from the point to the focus being constant, it's the difference of the distances, which has some useful applications in location detection systems. All right, let's take a look at how to sketch, though. That's the thing we're focused about. We're not going to use any of this distance to the focus points and everything. All right, so same procedure, though. We're going to gather the x's together. So that's 16x squared plus 32x. We've got minus 4y squared plus 16y, and I'll move this 64 to the other side. We'll factor out the leading number, which in this case is 16, and that'll give me x squared plus 2x. I'll leave a spot to complete the square. I'm going to factor out the negative 4, so I've got minus 4 out here. And then this is y squared, which makes this plus 4y, so that becomes the negative 16. Leave a spot to complete the square. So we're going to have 16 and then an x squared term from completing the squared minus a 4 times a y perfect square, right? We'll do the completing the square procedure, same as before. So we take this number here, 2, positive 2, cut it in half with its sign. That 1 squared gets put up here to make a perfect triangle to match. This one is times 16, so since we added a 16 on this side, we have to balance it with a 16 there. And then the same thing here, this positive 4 gets cut in half to a 2. 2 squared is 4, that got added, and so that means we've got this 4 times a negative 4, so we put a negative 4 on this side, we have to balance it with that's a negative 16. So we balance it with a negative 16, and we end up with a 64 on this side. Okay. So because we have a minus here, this is a hyperbola. The next thing is to get a 1 on the right side. So we would divide these by 64. And let's see. That's going to give me, yeah, let's write it here. So 64 divided by 16 is 4. So that's x plus 1 squared over 4. Minus y plus 2 squared over 16 equals 1. And that means the center of this object is at x is negative 1, y is negative 2. Right? And let's see, we're going to think of this number as being 2 squared and this 16 as being a 4 squared. All right, so we sketch it. We make our axes. We go to, let's see, x is negative 1, y is negative 2. Right? Is that right? I think I messed something up here really quickly. Let me make a quick change here before we get any further. I said it, but I didn't write it. When you factor a negative out, this has to become negative so that this ends up being positive, which means this is y minus 2. This is y minus 2, which means this is plus 2. So everything else is the same except we've got that. All right. So that means that our location is slightly different. It is negative 1, positive 2 for the center of the object. Sorry, going a little too quickly there. We're going to go a distance of 2 in the x direction. So 1, 2 in the x direction, 1, 2 in the y direction, or the other x direction. And then the 16 is 4 squared, that's under the y. So we're going to go up and down 1, 2, 3, 4. Down 1, 2, 3, 4. Okay, but instead of drawing an ellipse to those points, we're going to make a box. And then we're going to draw asymptote lines that go from the center through all the corners. This. Then we have to figure out which type this is. So the x term is positive, so that means it's going to open in the x direction. So that means we're going to start at the edge of the box here at that vertex. And then we're going to draw this approaching those asymptote lines and also on this side. So this would be the hyperbola for this case. Okay, one last one. You can try pausing the video and trying this. This is our last example. Okay, so we gathered the x terms together and the y terms together. Move the 29 to the other side. Factor out the leading 9, so that's 9x squared minus 2x, leave a space for completing the square, minus 4, this will be y squared, let's see, plus 2y, right, so that, no wait, plus 4y, because that's a 16, right? Yes, plus 4y, right, so negative 4 times positive 4 will give me minus 16, yep. Now we will complete the square. So we've got, let's see, 9, an x perfect square, 4, and a y perfect square. So we'll take the minus 2, cut it in half to negative 1, square it, which is positive 1. That times 9 is 9. That means we have to balance with the 9 over here. Take this positive 4, cut it in half to positive 2. 2 squared is 4, but that 4 is times a negative 4, so that's a negative 16 to put over here. And that means we have got a new number of negative 36 over here. So what happens if you end up with a negative? Well, we go ahead and divide by negative 36, everything. And so when you do that, you're going to get, this is x minus 1 squared over negative 4. And then, let's see, this is going to be minus y plus 2 squared over negative 9. Equals positive 1, but that means that since this is a minus minus, this is actually the positive and this is negative. So this is the same as saying we have negative x minus 2 squared over 4 minus y plus 2 squared over 9 equals 1, which just means I reverse the order of these. So we end up with y plus 2 squared over 9, that's the positive term this time, minus x minus 1 squared over 4 equals 1, which means the center of this object is that x is 1, y is negative 2, right? And this number below the y is a 3 squared, and below an x is a 2 squared. All right, so now we can graph that, x, y. Let's see, we want to go to the location positive 1, negative 2. There's the center of the object. Okay, we're going to go 3 in the y direction. So 1, 2, 3. 1, 2, 3 in the y direction. And then we're going to go 2 in the x direction. So 1, 2 in the x direction from the center. 1, 2. We will make our box. Up there, we'll make our box. We'll put our asymptotes in there. And then we'll draw the curve. Now for the curve, we have to know which one's positive. In this case, the y is positive, which means it opens in the y direction. So that means we'll go to the edge of the box, and we'll have a curve that wraps towards the asymptotes and also on the negative y direction, something like that. And that's how you quickly sketch conic sections without a calculator. All right. Right, so there's a lot to know. The main thing is how to recognize what do we have. If there's only one squared term, it's a parabola. If there's two squared terms with the same sign, it's an ellipse. If there's two squared terms with different signs, it's going to become a hyperbola. One squared term here makes this one's a parabola. Two squared terms, x squared and y squared with different signs, that one's a hyperbola. And if you have two squared terms with the same sign, that would be an ellipse, but the special case where the coefficients of the squared terms are the same, that one becomes the circle. So you should be adept at, or become adept at, quickly recognizing what sort of shape we have. And this is just a sheet that I had from when I taught Honors Algebra 2 with all the information, but like I said, we're only really focusing on this, the standard forms, so that we can sketch. All this other stuff we really don't need at this point in the class. Right, so that should be enough to allow you to quickly do the homework to practice conic sections.